by your mutual gravitational attraction. So we and the Andromeda galaxy, 2 million light years away, we are falling towards one another, even in the middle of the expansion of the universe.
By the gravitational pull between you both. Thus, even in the midst of the universe's expansion, we are falling into the Andromeda galaxy, which is located 2 million light years distant. Two giant galaxies in our cosmic neighborhood, the Milky Way and Andromeda, are headed toward a gradual but eventual collision. The Milky Way has 400 billion stars, but this has long been known, and each galaxy is, let's say, around the size of the Milky Way. Others are larger, others are smaller. Light travels across a galaxy in 100,000 years. The time frame for this enormous catastrophe may be shorter than previously believed, according to new study. What does this signify for our solar systems and galaxies' future? A peek at the Milky Way up close. In the night sky, the Milky Way may appear like a hazy, smooth band, but it is actually a massive, dynamic structure. It has a barred spiral form, meaning that a center bar-like structure composed of stars with outward extending, curving arms is present. Massive clouds of gas and dust, luminous nebulae, and star-forming areas abound in these arms. Stars travel hundreds of kilometers/s around the core of this cosmic disk. Our solar still needs around 200 million years to complete one full orbit around the galactic center, even with those tremendous speeds. The Milky Way's galactic core is around 26,000 light-years away from us. Sagittarius A is an extremely large black hole located in the center of our galaxy. Its mass is almost 4 million times that of the Sun. The majority of black holes, particularly those in galaxies' cores, do not actively consume all local matter despite their reputation for being extremely destructive. Instead, their strong gravity mostly affects the orbits of nearby stars. A star or gas cloud may be drawn in if it approaches too closely. If not, the black hole may remain silent for extended periods of time. A galactic ring of older stars and globular clusters envelops the Milky Way. Globular clusters are close-knit, frequently extremely ancient star groupings. Some are nearly as old as the cosmos itself. Astronomers use these clusters, which circle the galaxy beyond the main disk, to better understand how the Milky Way expanded over billions of years. According to studies, our galaxy has absorbed a large number of smaller galaxies in the distant past, leaving behind remnants in the form of star streams on the halo's periphery. Satellite galaxies orbiting the Milky Way are located outside the halo. The southern hemisphere's melanic clouds, both big and little, are the most well-known. On very long time periods, these irregular dwarf galaxies might be drawn in and united with the Milky Way. The Sun, our home star, is located in an area known as the Orion Arm or Orion Spur, about 2/3 of the way out from the Milky Way's core. This area is not too near to the center black hole or intense star-forming regions, thus it is rather calm. Earth also exists there. There are at least a few 100 billion stars in our galaxy, although other estimates put the number far higher. As more data becomes available from projects and new telescopes, astronomers continue to work to improve these figures. The significance of the Andromeda galaxy. One of the brightest galaxies visible from Earth without a telescope is the Andromeda galaxy, or M31. It is located around 2.5 million light-years distant, which is quite far by terrestrial standards, but very close by cosmic ones. Similar to the Milky Way, Andromeda is a spiral galaxy, albeit it is frequently claimed to have a greater total diameter. Andromeda may have greater mass, according to certain observations, although the two galaxies may be closer in mass than previously believed. In any case, it is the largest in the local group, which also consists of around 50 smaller galaxies and our Milky Way. Andromeda has characteristics with our galaxy, including a brilliant central bulge and several spiral arms that contain massive gas and dust clouds, as well as numerous stellar nurseries where new stars are formed. It is thought that Andromeda has a very enormous black hole at its core, with a mass that may be on par with or more than that of Sagittarius A in the Milky Way. In addition, Andromeda is surrounded by a network of globular clusters and is surrounded by dwarf partner galaxies. Astronomers questioned whether Andromeda was a distinct island universe or merely a nebula in the Milky Way at the beginning of the 20th century. The resolution was obtained by monitoring Cepheid variable stars, which are unique stars in the Andromeda Nebula whose fluctuating brightness may be used to calculate distances. Andromeda was shown to be a separate galaxy when scientists discovered it was millions of light years distant. Astronomers are interested in Andromeda for a number of reasons. We can thoroughly examine its structure, since it is close enough. We can learn more about the birth of particular star types by observing Andromedas. Star-forming regions. In order to forecast what could occur when the two galaxies merge in the far future, researchers also monitor Andromeda's speed with respect to the Milky Way. For a while, astronomers thought Andromeda was traveling at a speed of around 120 kilometers per second toward us. These measurements have been improved with the use of better instruments. However, it is still evident that Andromeda is headed for a collision or is close to one with the Milky Way. More generally, the local group is traveling across space while being drawn by the gravitational attraction of other massive cosmic formations. However, that doesn't make the major event that will happen in billions of years any less significant. What causes galaxy collisions? When two or more galaxies become close enough to one another that their gravitational attraction starts to draw them in, a galactic collision occurs. However, collision may conjure images of stars colliding in frantic explosions. There is a lot of vacant space between the majority of stars and galaxies. As a result, stars may move past one another without colliding directly. Nevertheless, a merger causes the galaxies as whole to become warped and twisted, a process that is both aesthetically pleasing and important from a scientific standpoint. Slow, calm collisions might give way to violent, fast-paced accidents. Galaxies are more likely to combine and grow into larger ones when approach speeds are lower, maybe a few hundred kiloohms per second. As gas clouds collide and collapse into newborn stars, these collisions may result in star formation bursts. Streams of gas and stars are thrown into broad arcs by tidal forces from the combined gravitational pull, occasionally producing shapes resembling tails. If the two galaxies had roughly the same mass, they would eventually merge into a single, cohesive entity over millions of years, frequently becoming an elliptical galaxy. In more severe circumstances, a collision may be more violent as galaxies approach one another at 1,000 kilometers per second or faster. In less time, the galaxies can be torn apart by the forces of gravity. While some stars could be flung into cosmic space, others might join odd or twisted formations. These occasions may not always result in a tidy merger. Alternatively, the galaxies could remain as dispersed fragments that gradually drift apart, their forms irrevocably altered. Scientists observe instances of galaxy collisions in the night sky to learn more about them. Numerous interacting galaxies at various phases, from first contact to final merger, have been caught by telescopes both on Earth and in space. For instance, the lengthy tidal tail loaded with stars is a well-known feature of the antennae galaxies in the constellation Corvus. The Mice galaxies are another well-known pair. They get their name from the long tails that tidal forces produce. Astronomers may recreate potential outcomes for the Milky Way and Andromeda and get further insight into the development and evolution of galaxies throughout cosmic time by observing these encounters. The function of dark matter in galactic interactions. There are other elements at work when two galaxies collide besides the observable stars, gas, and dust. It is believed that dark matter, which emits no light or other electromagnetic radiation, makes up the majority of a galaxy's mass. By observing the orbital velocities of stars around the galactic core, scientists initially discovered that galaxies held vast quantities of invisible matter. The stars close to a galaxy's edge were traveling too quickly for the mass that is visible to us to account for. This suggested that the gravitational attraction keeping those stars in orbit was coming from something else, dark matter. The precise nature of dark matter is still mostly unknown. According to physicists and astronomers, it is made up of a particle that doesn't interact much with ordinary matter. But like anything with mass, it exerts gravity. The dark matter halos of each galaxy may flow through one another, nearly undisturbed during a galactic collision. This halo collision can nevertheless influence the speed of stars and gas, influencing how the galaxies ultimately merge, because dark matter does not collide and disperse in the same manner as regular matter. Visible and dark matter components are both used in simulations of colliding galaxies. Growing processing power and improved data from enormous telescopes have made these computer models considerably more realistic. By running these simulations in fast motion across billions of years, scientists may enter variables like mass, velocity, and the dispersion of stars and dark matter. They may view the residual galaxy's ultimate form and contrast it with actual observations. Our understanding of how galaxies accumulate throughout time is improved by this. Dark matter not only contributes to collisions, but also forms very large-scale clusters known as cosmic webs or filaments. These filaments frequently meet to produce galaxies. This explains why groups of galaxies seem to be connected over hundreds of millions of light years in a massive cosmic web. Collisions and mergers are crucial components inside that web. They propel the expansion and development of galaxies, recycle gas to create new stars, and occasionally cause supermassive black holes at galaxy cores to erupt violently. The silent hand directing a large portion of this activity is the gravity of dark matter, which serves as a reminder that the universe is considerably larger than what we can perceive calculating collision times, velocities, and distances. Scientists require precise distance and velocity data in order to predict when and how galaxies will collide. In astronomy, standard candles such as Type A supernovae or Cepheid variable stars are a key tool for determining distance. There is a recognized correlation between seen brightness variations and true brightness. Thus, astronomers may determine their distance from Earth by observing how brilliant stars look. Type 1 supernovae are helpful for measuring even longer distances because of their steady peak brightness. After determining the distance to a galaxy such as Andromeda, astronomers look at its blue or red shift. A galaxy's light moves toward the red end of the spectrum while it is traveling away. If it is approaching us, redshift. The blue end is where the light shifts, blue shift. Astronomers can determine the galaxy's speed in relation to us by measuring the amount of light shift. Because Andromeda is blue shifted, it is moving toward us. The probable course of the collision has been improved by precise measurements of the Milky Way and Andromeda stars. According to early projections, a collision would occur in around 5 billion years. That has been reduced to about 4 billion years by more precise observations and simulations. Given the enormous timescales involved, this discrepancy may appear insignificant, even if there is still some disagreement over the precise timing. However, that is a big development for astronomers. By taking into account the known masses, velocities, and angles of approach of both galaxies, they simulate their gravitational dance to arrive at these estimations. It is anticipated that the galaxies would pass through one another a few times during the collision before being drawn back together by gravity. After the first closing, it might take a few billion years for the ultimate merger to occur. Tidal tails and star arcs will arise as a result of the distortion of the spiral arms and galactic disks over time. As the impact compresses gas clouds, massive star formation explosions might occur. The majority of models predict that the merging system will eventually resemble an elliptical galaxy. The future galaxy has been jokingly dubbed Milky or Milk Armada by some scientists. It's unclear if that moniker will catch on, but it reflects the lighthearted tone of many cosmic nicknames, both planet and star development. Gas clouds from merging galaxies are pulled into new regions, where the pressure from the collisions makes them denser. Star formation waves are triggered by this. These are known as starbursts by certain astronomers. Many hot, massive stars are created during starbursts, and these stars have a propensity to burn up rapidly and die in supernova explosions. These explosions release energy and heavy elements into the surrounding gas, which can either drive gas out of the galaxy altogether or fuel more star formation. New planetary systems may also form close to these star-forming zones. The environment is rich in chemical components, even though it may also be chaotic. Carbon, oxygen, iron, and other heavier elements are essential for creating complex molecules and solid planetary surfaces. The next generation of stars and new planets may arise as a result of collisions recycling and redistributing those materials. The evolution of galaxies over billions of years is largely influenced by this cosmic recycling, but collisions can also deplete a galaxy's gas supply. A large amount of gas may be ejected into intergalactic space if the collision is strong enough to stop certain galaxies from subsequently producing new stars. The resultant merging galaxy may eventually contain only older stars with little fresh fuel available to generate newer ones if too much gas is wasted. This is one of the reasons that elliptical galaxies, which frequently originate from spiral galaxy mergers, typically have more ancient red stars and less active star creation than the bluish spiral star-forming arms. In a galactic collision, not every single solar system is destroyed. The primary impact that stars encounter because to their extreme separation from one another is the modified gravitational field of the united galaxies. Large-scale orbital changes might result from that, although direct star-on-star collisions are still very uncommon. Orphan stars that yearn for a galactic home may result from the occasional tossing of whole star systems out into the void between galaxies, the very large black holes in the core of galaxies. The presence of a very large black hole at the heart of both the Milky Way and Andromeda is a key characteristic. The mass of Sagittarius A in the Milky Way is several million suns, but the mass of the one in Andromeda may be at least that much, if not more. The core black holes of two merging galaxies progressively move toward the center of the newly formed galaxy. They release gravitational waves when they spiral closer together over an extended period of time, possibly billions of years. They could eventually combine to form a single, even larger black hole. There would be a strong gravitational radiation explosion from such merging. The capacity of a black hole to feed relies on how near matter is to it, despite the fact that most of us imagine them as vacuum cleaners that absorb everything in their path. Swirling gas and dust may move toward the center during galactic mergers, occasionally feeding the black hole and causing it to flare up as an active galactic nucleus or quasar. This implies that it has the ability to emit dazzling energy jets that are visible for great distances. Future star formation may be impacted by this activity's ability to heat and push gas out of the galactic core. Black hole collisions continue to be a major focus of astrophysics study. Observers of gravitational waves seek to identify waves resulting from the merger of smaller black holes, which range in size from a few to several hundred solar masses. Future space-based sensors or particular timing studies of particular pulsar types may be able to detect the gravitational waves at longer wavelengths produced by the merger of extremely large black holes. Finding out how massive black holes merge will help us understand how galaxies have expanded throughout cosmic time. Astronomers predict that the last black hole merger in the Milky Way and Andromeda collision might occur many years after the star disks have already fused. This might extend to tens of billions of years, according to some calculations, depending on how rapidly the black holes can lose their angular momentum. By then, it's likely that the united galaxy will have changed into an elliptical structure with no apparent spiral arms, the solar system's future in the collision. What will happen to our own solar system when Andromeda and the Milky Way begin their gradual gravitational tango is a major worry. There is very little chance that the Sun will physically collide with another star due to the great distances that separate them. Our orbit around the galactic core is probably where the biggest change is occurring. While some stars may settle into new orbits closer or distant from the merging galaxy's core, others may be thrown out into intergalactic space by the combined system's gravity. Different results have been simulated by scientists. One option is that the solar system is still there in the new galaxy and keeps up its steady orbit. It's also possible that our star system might be sufficiently pulled by the merger's gravitational pull to be expelled. The Sun and its planets, including those that are still there, would be separated from the dazzling light of the galactic arms and drift through cosmic darkness if that ejection took place. But we must also keep in mind that long before this impact occurs, the Sun itself will experience significant changes. Our Sun will become brighter and hotter enough to burn away the water on Earth in 1 to 2 billion years. Metals on the surface could start to melt in another billion years. The Sun will turn into a red giant in 5 or 6 billion years, which might swallow Earth and other inner planets. Our world will become uninhabitable even if it is not completely destroyed. According to this chronology of star evolution, the collision with Andromeda is not as urgent as the solar system's eventual fate in terms of human life. The Sun could be nearing the end of its existence, or even have turned into a white dwarf by the time the galaxies have completely fused. Therefore, surviving the Sun's development is the larger challenge for any life forms that may yet exist. Instead, focus on the Sun's life cycle and how it affects Earth, rather than star-on-star collisions during the galactic merger. About 4.6 billion years ago, a cloud of gas and dust in one of the Milky Way's spiral arms collapsed to become the Sun. In its core, it burns hydrogen into helium, much as other ordinary stars. This process emits the light that warms the Earth and releases energy that keeps the star from collapsing due to gravity. The Sun will eventually enter the red giant phase by fusing helium and maybe other elements when the hydrogen in its core runs out. During the red giant stage, stars like the Sun expand because their cores heat up and shrink, while their outer layers becoming thinner and colder. Mercury, Venus, and maybe Earth are among the inner planets that the Sun is most likely to swallow or severely sear at this time. Different detailed models have different timelines for when Earth will be completely devoured or reduced to a burnt cinder, but the end result is always the same. The planet will no longer support life. However, the Sun's output will progressively rise before then. The Earth's climate might drastically shift with even 10% or 20% additional solar energy, making it excessively hot and drying out the oceans. That is anticipated to occur in 1 to 2 billion years. The Sun will shed its outer layers of gas after the red giant phase, leaving behind a white dwarf, which is a dense core. This white dwarf won't combine elements in its core, but it will still sparkle with residual heat. Over millions of years, it will eventually get dimmer. Given these realities, mankind would probably have to depart Earth long before Andromeda shows up for its cosmic encounter if it were still present in any type of advanced civilization. The Sun's alterations in the next 1 to 2 billion years will eclipse the collision timeline of around 4 billion years from now. Earth may resemble a scorching desert or a molten wasteland long before galaxies collide, and it may be completely different after 4 billion years. Prospects for future civilization and interstellar travel. The possibility of departing Earth for other star systems or galaxies is frequently brought up in conversations about the distant future of humans and other life forms. A civilization would have to migrate if it wished to survive the end of the Sun's habitable phase, despite the fact that this could seem like pure science fiction given our knowledge of long time scales. This might entail moving to farther off planets or stars, or possibly building enormous space habitats. If it encircled a star, the idea is frequently referred to as a Dyson swarm or Dyson sphere. There are several obstacles in the way of any interplanetary or intergalactic travel endeavor. Even light takes years, centuries, or longer to travel between 2 points because of the vast distances. Millions of light years cannot be traveled in a reasonable amount of time by traditional rocket propulsion, since it is just too sluggish. Among the theoretical concepts are starships propelled by antimatter, nuclear fusion, or even speculative warp motors that would change space-time. These concepts rely on technology that we do not yet possess, may not be able to create, or may not be compatible with the physical laws of the cosmos. However, who can predict what future civilizations would accomplish given a period spanning millions or billions of years? There may be methods to move over long distances if one believes that life and technology will continue to advance. An intelligent civilization may be able to spread information or life elsewhere only by imagining the possibility of sending robotic probes. The most pressing concern before to the collision with Andromeda is the sun's life cycle. If life persists, our descendants could migrate to colder or farther off worlds. They may have to reside on worlds near younger stars when the sun aged. Humanity, or whatever it has developed into, may be dispersed throughout the Milky Way by the time the galactic merger is visible. Residents in the far future may be able to observe the crash from a safe distance, maybe using advanced devices that are currently unthinkable. Additional noteworthy crashes. Although we are most familiar with the Milky Way Andromeda collision, galactic mergers are occurring all throughout the cosmos. Images of galaxies colliding or merging are frequently captured by observatories. The antennae galaxies NGC 438 and NGC 439 are two well-known instances. These are located in the constellation Corvus, about 60 million light-years distant, derived from the lengthy tidal tails that emanate from every galaxy. They give a crystal-clear illustration of two spirals falling. Bright knots of star formation produced by the collision occupy the middle portion of this pair. The mouse galaxies NGC 4076 are found in the constellation Coma Boneses, about 300 million light-years distant. The lengthy tails that extend out like a mouse's tail are what gave these two spiral galaxies their moniker. Tidal forces primarily control their interaction. NGC 6240, about 400 million light-years away, there is another remarkable pair of colliding galaxies with two extremely enormous black holes that are now active and are predicted to join. Observations at several wavelengths reveal a tremendous gas outflow and significant starburst activity. Astronomers can put together the general sequence of events that take place when big star systems merge by examining these galaxies at various stages of merging. More in-depth observations of these interactions will be possible because to ground-based observatories with big mirrors in future and existing telescopes like the James Webb Space Telescope, they will aid in mapping the distribution of gas, the locations of star formation, and the ways in which the merging process affects black holes. Additionally, astronomers replicate similar real-world instances in a virtual setting using computer simulations. They modify variables like as the masses of individual galaxies, the dark matter distribution, and the approaches of the galaxies. Scientists may verify the best fit models by comparing the final images from the simulation with the real observed shapes of colliding galaxies. They may forecast how the Milky Way and Andromeda would appear at each stage of their ultimate merger with the aid of these models. The Milky Way's destiny is not unique. A key component of how structures in the cosmos come together is collisions. Bigger galaxies can combine again, while smaller ones can merge into larger ones. This cosmic process creates new stars, recycles stuff, and frequently sparks bursts of intense activity near very large black holes. Despite the fact that it sounds chaotic, it is only one more chapter in the lengthy history of the universe's evolution. We may learn more specifics about the precise course that Andromeda and the Milky Way will follow as they start their gradual transition to one giant galaxy as we collect more data and improve our methods. For the time being, we may wonder at how these occurrences demonstrate the dynamic essence of the cosmos we live in, albeit spanning unfathomable time spans. We appreciate you seeing another episode. For higher quality material, click on the video that is now displayed on your screen while you are still here.